Hi and welcome everyone. Today we start in our 2D MMORPG the first time developing something, and we will start with the world chat. First of all, since we start using the UDP custom library, I want to elaborate a little bit more about why we use UDP and not something like TCP or the REST API, for example, which is pretty common in web development. Then we will start writing the server. The code is already done and working, but we will go through the code and how everything works and explain it in detail. For scalability, this version of the chat server won't be scalable because we go one step after another. In the next video, we will make the chat server scalable. But if you can't wait for that, on GitHub, the development process is always way ahead of those videos. So you can always check this out, or you can join my Discord, and I'm really happy to help you. And if you learned something, please like and subscribe. And after that, we will write a very short chat client just in console. So no Unity today, sorry for that, but we would like to go slow but steady, and this way I can explain more things in videos more deeply and go into everything instead of crunching everything in front of you down, and you won't learn something. So TCP is in pretty much a lot of networking technologies like REST services and everything, the communication layer that is beyond REST or any HTTP or web protocol. The thing with TCP is TCP has the advantage that it has some kind of connection, so it knows which client is talking to which server and everything, and it's reliable, ordered, and has proper flow control. So reliable means when your package gets lost in translation, so it gets lost because you're connecting over the ocean, or some router from A to B is not properly sending your messages or is overloaded. Those things happen in the internet every time. Then TCP makes sure that the package gets resent, and we will take a look into that because that's also one of the problems TCP will occur for the things we plan to do. Also, TCP messages also come in order, so when the server receives them, it will make sure your application gets those messages in order. Flow control is basically when you send a lot of messages, you can, with the TCP, just spam messages to the network, and TCP will make sure to properly buffer them and don't overload the system. With UDP, you have none of those things. With UDP, you have no flow control. You can basically overload your network card, and it will start to have more package loss than before, and round trip and ping times will go bad and everything. You can do that in UDP. You have no control mechanisms which save you from things like that. Also, UDP doesn't know anything like connections, and also reliability. If your message gets lost in UDP, it's lost. There's no out of the box way for resending and everything like in TCP, and your messages will get out of order, which is also known as the term jitter, if you want to Google a little bit more about that. So the question that will come up is, why do we use UDP when TCP is so superior out of the box? The problem is that TCP is a general purpose networking protocol which is reliable, safe, and good to use. But in games, often data is very time-based. For example, a player position will change multiple times within a second for the game. Those messages need to get across as fast as possible, and it's also not very interesting if a position data gets lost. If one or two packages gets lost, it's not interesting if this, because the server basically is most of the time interested in the current position of the player and not what happens half a second ago. And TCP will always resend those messages even if those messages aren't interesting anymore for our server and the other clients. And that's really a big downside. And there's also in TCP something which is called Nagel algorithm. for now, let's say Nagel algorithm is waiting for your packages to get some size to send those packages out, because the TCP header is actually 40 bytes. Let's say we want to send X and Y position from a player. So that's, let's say, 8 bytes. If we don't do anything, it's 2 floats, which is probably 8 bytes. So we have 8 bytes of data and 40 bytes of header. And to not waste that much bandwidth, the Nagel algorithm just waits if more data is coming, and if more data is coming, it will combine those data together and send it in one bigger package to not waste so much bandwidth. There's actually a workaround for that. If you give your configuration a TCP no delay, then the Nagel algorithm basically is deactivated, and TCP will send out your packages as soon as you send them. So there's a way around that. That's not really the biggest issue, but this shows one thing TCP does, which actually is bad for the things that we want to do with our networking. The real issue with TCP is package loss. If your package gets lost with TCP, there's a lot of time wasted. And if you test those things on your machine or with a good internet connection, no, those things won't happen. But the problem is, if you put your game on Steam, there will be players who will use your game with a bad internet connection. They might not even know that the internet connection is bad, or your server is at a very far away spot from them, and the longer the package has to travel, the more issues will occur on the way. Package loss will happen. It won't happen in your test cases if you don't test against it, but it will happen in a real life scenario when your game is out there. Because of that, TCP is not good for that. The reason is how reliability in TCP works, and we take a very simplified look at that. It's more complicated than that, but this shows the core of the issue. On the right side, you see an image with a client communicating with a server. Connection is established, no handshake, everything is done, and the client sends packet 1 to the server. Let's say this is a player position, like I said, XY coordination where the player currently is. And when the server gets the message, it sends an acknowledgement. I got position or packet 1. Then let's say the client will send packet 2, but it will actually fail. So the packet will never arrive at the server. And how does TCP know that the package doesn't arrive? It's quite simple. It never got an acknowledgement, an ACK packet for those packets. So how long does TCP wait? It's usually 2 times the round trip time. Let's say you have bad internet connection and your ping already is 100 milliseconds. So a round trip time, sending a message to the server and directly getting it back, takes 100 milliseconds. Now, since the package failed, TCP will wait at least, in best case scenario, 200 milliseconds to detect that the package gets lost. Now, imagine you have a game and you just move right on your controller, and half of a second or 200 milliseconds, which is 1/4 second, is lost, and then TCP sends again package 2, because that's how the underlying system works. And it sends basically your player position, which is a 1/4 second old, and doesn't send your current player position because it has to resend package 2. And only if package 2 is acknowledged and everything is working fine, your next packages will go out. There's actually a window, and TCP is able to send multiple packages at the same time, but that would overcomplicate this example. But you get the idea. You sent the player position half a second ago or something, and it's totally not interesting for the server anymore. The server wants to know your current position, and for that, TCP is really, really bad. And let's say, how do we In UDP, we don't have something like reliability, but our UDP engine has to implement something like that. And let's show how we solve that issue. Since we have a lot of small packages, what we can do with UDP is, for example, we send package 1 and we wait for an acknowledgement package from the server. We have to build it ourselves and we have to send it ourselves because UDP itself doesn't do that. TCP itself does that really fine. But in UDP we don't have that, but we can build our own acknowledgement system, and server sends an acknowledgement and we know that package was successfully sent. What we can do, since our packages are very, very small, if package 2 failed and we want to send package 3, but we want to make sure that all packages go to the server side, we can basically just send package 3 and 2 together in one package. The server is then able to receive both packages and acknowledge both, and this way we can leverage the bandwidth that we have way better. And today we have a lot of bandwidth. If you compare, for example, with games 10 years ago, where an ISDN connection was, compared to today, very, very slow. You basically had to fight for every bit in your bandwidth, and today it's not that much anymore. Today the only issue is what happens when packages get lost and how do I get packages from A to B as fast as possible. And to solve this issue, we will use UDP. We will leverage a library for that, so we don't have to write the reliability thing and everything on our own. So this is covered for us, but still I wanted to explain why we do that. Thank you for being here, and let's check the source code. I checked out the source code and I messed up a little bit because when I was developing further, I changed the submodule. We have a submodule which is basically our UDP engine, and I changed the submodule. So if you go back to older versions of the code, you might here and there have to fix some references and everything, but nothing too crazy. What you want to do, because if you check out the submodule, at the latest version of it, I implemented async await pattern throughout the library, throughout the UDP library, and this version of the code can't cope with that, so you have to go back to fix ping pong issue, which is basically before async await was implemented in the UDP library. But don't worry, if you check out the latest version, everything is fine. So let's check out the source code. First of all, we check out what is available in our libraries. We have our UDP library, which is Reliable UDP. And we have Common Server. And in Common Server, we have a base UDP listener and a UDP manager listener. Those have some helper functions to work with the UDP library. For the UDP listener, this one is basically our entry point to the library, to the UDP library on our server side. It has functionalities like start the server on a given port, and then it uses the UDP library to start the server on a given port. It also has the close server, and we have to configure a listener when we start. So this is basically just a facade for our UDP library to make using it very easy. On base UDP listener, you basically have a listener which gives you the ability to basically listen for different events that can happen on UDP, and this is a base implementation. We will later use it to have some helper functions like here sending messages to one player or to all player that is connected to the server. The thing with this is a living entity. It will change a lot and dramatically throughout the development, but for now let's just use it as it is here, and it will change because there will be very many refactoring throughout the videos on this entity alone. And on common, which is basically shared between client and server, we have, for example, the protocol, which is how does the chat message look like. A chat message for us currently is just a plain message. It's just a string, and how do we detect that if something is a chat message? We start always with 1 byte of what is this message type. And with this 1 byte, we can distinguish what message will come. When we write to the network stream, we write 1 byte, which is a chat message, and then we write the message itself. On the other side, we have the read function, which does the same thing. It peaks. A peak is basically reading 1 byte, but don't consume the byte from the reader. So we peek, is this a chat message? And if that's not the case, then we will not read the message any further, because this is not something we are able to consume. And if it is a chat message, we will follow through, and we have to consume the 1 byte because we just peeked the byte, and it's still the pointer of the stream is still pointing to the message type. So we basically throw that away, and then we read the string which should follow behind the message type, and that's how we write our whole protocol. So if we want to, for example, increase this message type with a sender, for example, as a string, then we can go in here and write a put, and then we can also include the sender, and then obviously we have to read the sender. And we can do that for a lot of data types out of the box. So we have pretty much most common data types like byte, string, int, float, everything in there. Let's say, which might be not as obvious. Let's say we have you could whisper the message to multiple players, which doesn't make sense, but it's just an example. Let's say you have a list of string where you can send to. Give me a second. Let's initialize that, because if it's not initialized, we might get into trouble. Then you might want to send the count, and then for each send to entry in send to, you can write the entries to the stream. And on read side, you read the count first, which is an int in our case. We get an int, and then we read till the count is fulfilled, because we have to, and we add it to our we add it to our list. This is basically how we also can do lists and everything. That's how we write our protocol. There are many different ways to do this. There are even ways to automate it with protobuf and everything, but I like to do it by hand in this case, because I'm a single developer, and as a single developer there are not many ways to mess this up. So if you have to solve merge conflicts and everything within your protocol, it might get pain in the ass, but for me as a single developer, it's straightforward. So it's actually faster than protobuf and everything, but it's actually more error prone. So if I read, for example, if I have two messages here, and if I read in the wrong directory, so let's say I read message 2 first and write them in the other way around, then this won't work. So it's pretty error prone, and maybe not best practice, but I like to do it that way. So let's check out how the server code looks like. It's really straightforward. We use our facade to initialize everything, and we have a listener, and we give it a connection key, which is basically a hard-coded key that the library uses to establish the connection. Then we say we want to listen on port 333, and we want to update. This update is basically behind the scene. The UDP library has an event queue, and this update is basically consuming this queue. And then as long as we want to let the server run, we always update our events and consume them, and then we wait for 50 milliseconds. Let's check the listener, because the whole magic is working in the listener. As you can see, the listener is really straightforward for now. It just checks if we have a chat message, and if it read a chat message, it sends it to all persons that is connected to this server. So if we go through that, it checks if we are initialized, and then it writes the message to a UDP writer and send it to all. Pretty straightforward on client side, which is basically really hacky way to test things, because later we want to use the client in Unity, and then we will extract better client libraries for Unity to use. But this is the first test we ever do with the library. So we have a chat message here just for reusability, the same for the writer. Then we connect basically to localhost on port 3333, which is where the server is listening to. And then we do a connection. When we start to connect, the library set the peer connection state to in progress. And we wait as long as this is the case, and we have a maximum wait of 5 seconds. And so we wait maximum of 5 seconds, and if the state changes. The state will change to connected if the connection is established successfully. Then we have this update thread, which will update the events, which is basically like the update function on the server, which will run in its own thread, so that our UI thread, in our case our console thread, isn't disturbed. So we have another thread which is basically just updating all the time when events occur, that our listener gets those events. Yeah, let's finish that one first. Then if it's connected, we will read a console line. So when I write something on the console and press enter, the chat message is filled. If it's not filled, so if I just press enter, the client will actually disconnect and will close itself. But if I enter a message, then the client will write the message to the network stream. We have the listener on the other side, which basically on network receives. When it gets a message, it will write it to the console. So I have prepared everything to be multiple starter projects, so a client and the world chat server start when I press F5. Both are configured to just start as a application, so it's not in a Docker container or everything, it's just plain console application for now. Later we will add those to Kubernetes and everything. But to make testing fast and easy, we will do it like that for now. So we have the server which is running, and we have the client which is connected. If the client doesn't connect, let's do that first. If we do give it the wrong port and the client isn't able to connect, then the client will write connecting. So if it stops writing connecting, then we know that the client is connected, which is not the best way to do it. We could also write here console write line connected, but honestly, since this is just for testing for now, I don't care too much. Now it's not working, even though it should. Connect to 333, pretty fine. Now it's working. Networking is great, right? And if I write something, for example, hi, and I press enter, the message is sent to the server and the server sends connect hi to everyone. So when I press right click here and start a new instance, I actually have two clients now. I have the server and two clients. And if I write hi there, it actually both clients receive those. Hi, you too. If I write here, both receive those as well. And if I just press enter, the client will disconnect. This is the very first example and very basic in what we do. Let me really fast elaborate what it does again. The server listens, the server listens on port 333, has an update loop, and if a message gets in, it sends it to all players. On the client side, we basically connect. We connect, then we wait for the connection to be established. We have an update loop, and if something is getting written on the console, we send it. Our network library implements 4 different ways. We can send reliable, which is basically if no acknowledgement from the server comes back, then we will send it again. We have reliable ordered, which is basically a more game appropriate version of TCP. And we have unreliable, which is it sends it and whatever happens. And we have unreliably ordered. Unreliably ordered means every package gets a sequence number, and only if the sequence number is higher than the last one that we received, the next message is consumed. Let me explain that real fast in an example. Let's say we send sequence number 1, so package 1, and the server gets it. So for server, the client has, for server, the highest sequence number is 1. Let's say we send sequence 2 and the server didn't got it. It failed, so the highest sequence number on server is still 1. Let's say jitter happens and we send sequence number 3 and sequence number 4 pretty much very fast behind each other, but sequence number 4 arrives at the server earlier than sequence number 3. This can happen in networking. If packages take different routes or router get messed up with the queue, this happens. On server now, the highest sequence number is now 4, and when sequence 3 finally arrived at the server, it is ignored because it's below our highest sequence number. That's how unreliable, sorry, not reliably, that's how unreliably ordered works. So for example, if we use that for our player position, if the server already knows the new position of the player, it is not interested in any previous position of the player. That's one way we could achieve that with our library. That has another issue, but we will talk about that when we talk about player movement, because this would go too far for this video for now, in my opinion. So this is basically the first code we have written. If it was too fast, too slow, or you have any feedback for me, please leave a comment in this video or join our Discord and tell it to me. I'm very happy that you are here, and I hope you liked it and learned something. Have a good day.